Okay, I'm back with more flux. We're going to practice. This is supposed to be a cylinder, by the way. I tried to draw it like 3 times. It's terrible. We're going to practice with using flux. I'm going to do 2 practice problems, one with a cylinder, one with a cube. So when we're doing Gaussian surfaces, again, this would be true for any college level, like first year, calculus-based physics course. So there are very few of you, if any, that would go beyond this level with Gauss in college. So when we're using Gaussian surfaces in this first year, we do it with surfaces we can easily find areas for. We're looking at cubes, we're looking at spheres or shells, we are looking at cylinders, we're looking at sheets of charge. And this is why we don't really need calculus, because the areas of all of those things we should know or easily be able to find. So you use different shapes depending on what you're trying to enclose. For now, just kind of bear with me, the shape is given. So we have a uniform electric field in this problem. The electric field is running from right to left, okay? So, like so, all the way across the board. It's really piercing through. I'm not showing it very well, but it's piercing through. So it's coming into this face of the cylinder and out of this face of the cylinder. We often use cylinders to enclose like wires of charge. Sorry, my table gets Asher's over there still, and he's kicking it around. Okay, so the question in the hi, buddy. It says that this cylinder has a radius r, and the electric field. They didn't give us numbers in this one. We'll do one with numbers and one without. The electric field is just equal to E, and it's running as diagram from left to right across the page. So we probably have some large positive charge over here, some large source of charge. And so the question is, what is the total flux through this Gaussian surface? So the Gaussian surface is the cylinder. When we are working with things like cylinders or cubes, they have multiple faces, right? So we think of 3 different surfaces that electric field lines can be piercing. One would be right here, the like left circle part of the cylinder. 2 would be this, the body of the cylinder. And 3 would be this right face of the cylinder. So I am going to find the flux in all 3 of these surfaces, and then I am going to find the total flux by adding them, okay? So let's start with surface 1. The flux through surface 1 is equal to the electric field times whatever area that electric field is piercing. Here, we first say to ourselves, is the electric field, oh goodness, I better pick up Asher. He's kicking the table. Ash, man. Look at this mischievous boy. Okay, the electric field lines, first of all, we say, are they piercing the surface? And the answer here is yes. Just visualize it. So these field lines are running right into surface 1. So yes, they are piercing. Are they piercing in or out? And here we can see that they are piercing in to surface 1. So that's going to be a negative flux. And then we say, okay, well, what's the area that this is piercing? Surface 1 on the cylinder is a circle, right? So its area is pi r squared. So we say that the flux into surface 1 is equal to negative, because it's in, the electric field, which they just say is E, times the area, which is pi r squared. So that is the flux running into surface 1. Negative E pi r squared. And if they gave me numbers for those things, I could get an actual value. And the value is newtons per coulomb times meters squared. I didn't really get into the units there. Surface 2. Surface 2 is this outer shell of the cylinder, right? And so as it turns out, none of these field lines is piercing out of that shell of the cylinder. They're all just running parallel to it, right? So there are no field lines piercing surface 2. If you need to look in the book, maybe the picture is a little bit easier to visualize, because as you know, pictures are not my top talent in life. But the idea is, like, this is a shell, right? If you picture like a paper towel tube or something, lines running into it, none of those, even if it's skimming right on the surface, none of those is piercing out through the surface. And so we say that the flux through surface 2 is just 0. There is no flux. If you want to think about the angle between them, the angle, well, actually, never mind, because I don't want to get too into the trig. So I regret those words. I take it back. And then the third surface, the flux is equal to E times A. And let's look at that surface. This is surface 3. The field lines would be piercing through surface 3. They would be piercing out of surface 3. So that means it's going to be a positive flux. And that flux value is E times the area, which is pi r squared. Now, when we take these 3 flux values and we add them to get our total flux is just 0, right? And that makes sense for this surface. There's actually, well, this is jumping ahead to Gauss's law, which I've not taught, but there's no charge enclosed by this surface, right? The same amount of field lines that go in are equal to the field lines that go out. So the net flux, although there is flux here and flux here, the net flux for this entire surface is 0. So that's the idea of finding flux. Again, you see that if you go and look at this problem in the textbook, they'll use that calculus notation, but this is all that they are doing. So there's really no calculus involved. Now the other sample problem that they do is a cube, and this one is a little bit more involved. This is a cube with an electric field that is non-uniform. So they have a cube. I'm stressed out about drawing this cube. I really might tell you to look at the book. Maybe I'll just, here's what we'll do. Okay. Surely I can draw a cube, right? The cube goes from 1 to 3 in x. That's what's important. So here's my cube. Oh boy. Something like that. I don't know. Like that's a cube. This is x equals 1. This is x equals 3. This is y equals 0. This is y equals 2. So it's a 2 by 2 meter cubed. And then there's z. We don't really care about z because it doesn't ask us. Okay? So that's my picture. Again, there is a better picture of a cube in the book where they have talents that I do not possess. And for this cube, it has I'm going to sneak down and read. The book's right here. It has a change in electric field. So it says a non-uniform electric field given by this function, E is equal to 3.0 3.0x, that's what makes it change. And I, is it plus 4 in J. Okay, so we have a non-uniform electric field given by this function. So this means the electric field in x, because I is our x, right, changes. It's equal to 3 times x. And y is actually constant, it's just 4. So the electric field in y is constant. And there's no electric field given for z. So we just have I and j. They don't give us anything for k, so we're not going to deal with it. And so the problem asks us to find the electric flux through the right face, the left face, and the top face. Okay? So we want to find the electric flux over here. We'll do that first. Well, through here and through here. Okay? So left, right, and top. Let's actually start with the top. I said I was going to start in X, but let's start with the top. So the electric flux through the top face is what I call E3, right? An electric field, or I'm sorry, I'm writing the wrong symbol, girls. I'm not going to start over. There we go. Electric flux through 3 is equal to the electric field times the area that it pierces. Okay, so we only care about, because this is in Y, right? Any field in X is running like this, back and forth horizontally. It is not piercing this face. The only thing piercing this face is the electric field that is in Y. And that is given as 4.0. It's the constant value. So 4 newtons per coulomb is the electric field in Y. It is positive, which means it's running up, right? We call that positive. So it would be piercing out of face 3. So we say that the electric flux through surface 3 is equal to the electric field, which is 4 newtons per coulomb, times the area of phase 3, which is, this is a 2 by 2 cube, right? So 4 meters squared. And so this gives me an electric flux that's positive, again, because I'm piercing out of that surface. It gives me an electric flux of 16 newtons times meters squared per coulomb. This is the unit for flux. So I didn't have to do anything really with this function. I just need to identify the piece that's in Y and plug it in. Now, let's look at, let's look at the other two faces. Let's look at the left face. So we'll go with 1. So the flux through surface 1, again, is equal to E times A. The flux in X, because the Y would be running like this. None of the Y is piercing 1. We only care about the electric field in X. So the electric field is equal to 3 times X. Now, although this looks like a varying field, on face 1, every point on face 1 has a value of X is 1 meter, right? So the electric field on the left side of this cube is a constant 3 newtons per coulomb, because that X value is just 1. The electric field in X is also positive, which means it's running from left to right. So we would say on face 1, the electric field is piercing in, so I'm going to make it negative. And I put in its value, it's just going to be 3, because that X value is 1, times the area, which is 4 for all the faces of the cube, it's the same. So the electric flux on face 1 is negative 12 newtons times meters squared per coulomb. Again, negative, because if we imagine these field lines being running in the positive direction, they're piercing into face 1 and out of face 2. And now we're going to go over to face 2. So the flux through the cube face 2 is equal to the electric field at face 2 times the area at face 2. The electric field is piercing out of face 2, so it's going to be a positive electric field. And we go to this function, 3x. At face 2, x is 3 meters everywhere. So the electric field at face 2 is 9. 3 times x would give me 9 newtons per coulomb. I'm going to multiply that by the area, 4 meters squared, and I get a positive 36 newtons times meters squared per coulomb. So the flux through the top face is positive 16. The flux through the left face is negative 12. The flux through the right face is 36. If they asked me to find total flux of these 3 surfaces, I would just add them. Maybe they would ask me to take the bottom into account, whatever. But this problem just had us go through and individually look at each of the surfaces. So again, flux. When you go to the textbook, because I am going to encourage you to read along with these notes. When you go to the textbook, and even when you look at my PowerPoint slides, because I use their notation, you see this, kind of nasty calculus notation all over the place. But all we're doing is taking E and multiplying it by A. If the field lines are piercing into a surface, then we say it's a negative flux. If they're piercing out of a surface, we say it's a positive flux. Anytime they're running parallel to a surface, like in that cylinder example, that would be a place where you see 0 flux. And that's it. So your first homework set, which we're going to go over together in class on Wednesday, just deals with flux. We're not going to get into how we can use it yet and what Gauss's law would say about it. It's just finding flux and getting comfortable with that concept.